Hello, my name is Zach Maldonado.
I'm Beza.
My name is Matthew.
And this is Samaya presenting an electrifying explanation of circuits.
In this circuit diagram, we are given a problem where we need to calculate the total power absorbed and delivered throughout the circuit, the closed circuit. We see that we have no resistors, so we need an equation that will help us be able to find the power of each of the indicated devices.
So the unknowns that we're going to be talking about for our section are, and we only have one, is the power in the different parts of the circuit, and the power in our circuit is going to be represented by watts.
Our knowns are voltage in kilovolts and current in milliamps. We also have no resistors.
We can assume that looking at our circuit, we have no resistors and is a closed circuit, so we're going to be following the conservation of power, so the total absorbed and total delivered should be the same value.
We will keep the current values in units we have been given since 1 kilovolt is equal to 1000 volts and 1 milliamp is 0.001 amps. The units we will have now will cancel out the zeros, and we will still end up with watts as our unit for power.
To calculate our total energy absorbed and delivered, we need to use Ohm's law, which the definition is that electrical power is the product of volts times amperes. Ohm's law also tells us that if the current is going through the positive terminal, we leave the equation as is. But if it flows through the negative terminal, we put a negative sign, so the current keeps a positive direct flow.
To find the total power absorbed or delivered in element A, you will multiply the current of A times the voltage A, which would be 0.6 milliamps times 150 kilovolts. This should give you that element A absorbs 90 watts.
For device B, we're just going to plug in the amp and the voltage. This will give us a final answer of 210 watts.
For C, we need to be aware that our electricity is moving into the negative terminal. So we need to add a negative sign to our equation. This will give us an answer of 80 watts.
So to get the power of D, you plug in your voltage and current and you get negative 200 watts.
Now we will solve for element E. Since the current is going into the negative terminal, we will put a negative sign in our equation. So you just plug in the values, negative 300 times negative 2, which equals 600 watts.
So to get the power of F, we have to multiply the current of F and the voltage of F. And when you do that, you get the total value of negative 360 watts. All right, so right now we have our absorbed values, which are going to be PA, PC, and PE, and we have our power delivered values, which are going to be PB, PD, and PF. We don't have to write the delivered values as negatives anymore because we're just checking to see that total power absorbed and total power delivered. And when you add the absorbed values together, you get 770 watts. And then when you add all the total power delivered values together, you get 770 watts. And because these are both equal to each other, we can say that it would make sense that both were able to equal 770 watts as the circuit is closed. The conservation of power tells us that both absorbed and generated powers are equal, and our circuit shows this.
The concepts presented through problem A can be applied to various real-life situations, such as providing cost-efficient ways to make machinery that can satisfy consumers' needs. Thus, it's important to find the power of a system in order to know the cost of running that machine. Therefore, by identifying the cost of running that system, we're able to find alternative ways to lower the amount of power we use to increase our profits and savings. Many companies use this type of mentality to provide consumers with cheaper goods, at the same time finding affordable ways to profit from these goods. As Jesse J once said, it's all about the money.
In conclusion, we found the total power absorbed and delivered in the circuit for all 6 devices.
Our known variables were the voltage, current, and the fact that there were no resistors in the system. Our unknown variable is power measured in watts. Our assumptions were that because the circuit is closed, then the system will follow the conservation of power. The units of kilovolts and milliamps would not affect our units of watts of power because zeros would cancel out.
So the only method that we're going to be using with our question is going to be this one right here in Ohm's law, the power equals current times voltage.
In conclusion, we take the power that we find for every single device, we organize them by taking all the positive values, which means they are absorbed, and all the negative values, which means they are delivered. We add them each together, and we see that they are both equal. Therefore, they have maintained conservation of power, but this is the total power that we got absorbed and delivered.